Okay, welcome everyone to this week's CDAC webinar. Today it's a great pleasure to introduce Professor Jung-Fu Lin from the University of Texas at Austin. Afu is a longtime member of the CDAC community going back to his graduate school days. Afu is a geoscientist and mineral physicist who specializes in high pressure temperature experiments, principally using diamond cells, and has made important contributions to understanding the interiors of the Earth and other planets through his research and his really quite numerous publications. He's also worked and extended his interests and talents to high pressure material science, including applications to energy materials. Afu obtained his PhD from the University of Chicago in 2002, moved to Carnegie as a postdoctoral fellow, and then was appointed as a CDAC research scientist for 3 years before joining Livermore as a Lawrence Fellow. And in 2008, Afu was appointed assistant professor at UT Austin, and there he built an impressive high pressure laboratory and rose through the ranks, becoming full professor in 2019. Throughout his research career, he's been interested in the behavior of iron and its role in planetary interiors. And that's a continuing theme of his work. And we're pleased that hopefully he'll give us an update on those efforts in this talk. So welcome, Afu.
Thank you so much for such nice introduction, Ross. And it's a great honor to be given this talk. Like Ross mentioned, I started my career as a postdoc and a research scientist in the CDAC program. So it's also good to see some familiar faces here in this meeting. So I thought I would like to update you about the transport properties of ion alloys and how that actually help our understanding of the energy sources and the geodynamo of the Earth core. So this presentation is derived from a number of publications through collaborations with a number of key collaborators. We got a funding from National Science Foundation CDAC program with Ron Cohen, Alex Goncharov, and Peter Driscoll to work on transport properties of ion alloys under high pressure, high temperature conditions. So I thought some of you may not familiar with this topic, so I'm going to give you a little bit more extended introduction on the geodynamo and the origin of the magnetic fields. With the geodynamo, we need some energy sources to power the geodynamo. So I will be mainly focusing on the transport properties, electrical and thermal conductivity of ion alloys under high pressure, high temperature conditions relevant to the Earth outer core, and then derive the energy sources, basically the thermal energy versus compositional energy sources from there. So from this type of studies, we can then kind of try to extend it to kind of better understand not only the magnitude of the energy sources that we need to power the geodynamo, but potentially the variations in the energy sources that are caused by the heat flux heterogeneities at the lowermost mental regions. And I will also try to extend the discussion into planetary science. All right, so in this cartoon here, this is a snapshot of the Earth interior that we know of today. We know the Earth interior is layered, and this is the region that we are focusing on today. So basically, in the Earth outer core, the vigorous convections of ion alloy generates a magnetic field. And with that in mind, there are energy sources that are needed to power the geodynamo. One energy source is actually the heat flux across the core-mantle boundary. So let's call this thermal energy source. And traditionally, we take this value QCMB at about like somewhere around 10, 13 terawatts. Just to give you a reference, the heat flux at the Earth surface is about 46 terawatts. And so this not only can power the geodynamo, but also provides important energy source to power the mantle convection as well as other geological events in the Earth, mantle, and the crust. So that's one energy source. And the second energy source is the compositional energy source from the crystallization of the Earth inner core that releases light element as well as latent heat into the outer core. So the Earth core is pretty far away from us, and it's also under extreme conditions. So sometimes it's kind of difficult for us to imagine the importance of the magnetic fields. Like we can actually look at the Aurora, which can be a telltale sign for a habitable planet. So the Aurora is the interaction between the Earth magnetic fields and the charged particles from the outer space. The existence of the Aurora also tells us that Ohmic dissipations, and without continuous energy source, that Ohmic dissipation, basically the magnetic field would actually disappear somewhere in about 10,000 years or so. So there's a continuous energy source, all sources in the Earth outer core. Another interesting geological observation is the magnetic reversals, and that tells us there are likely various energy sources through geological time. We probably have very good magnetic records dating back as old as about like 3.4 billion years. And based on the magnetic records from mid-ocean ridges, we see those kind of black and white stripes that actually tell us the reversals of the magnetic north and south poles over a period of about like 100,000 years or so. And those magnetic records reversals are well recorded in the past 30, 50 million years. All right, so we probably should look back at the very early beginning, the formation of the Earth, about 4.6 billion years ago. So the Earth was likely formed through collisions of small planetary bodies and heavy molten ion alloy then sunk down toward the center of the Earth to form the Earth liquid outer core. At that time, it was probably very hot and fully molten. Some elements, light elements, such as hydrogen, carbon, oxygen, silicon, and sulfur, also dissolved in ion and went into the core with it. There are also some radioactive elements that are dissolved in ion, such as potassium and uranium. Those radioactive elements can provide radioactive energy source to power the geodynamo probably continuously based on their half-life. The amount of their energy is very uncertain, but it's probably somewhere around like 1 to 2 terawatts also. Right, so we can actually use the melting curve of ion alloys as well as the phase boundaries of CDK materials to determine the we call geosome pressure temperature distributions in the Earth interior. And this is just one example to show you the pressure temperature conditions in the Earth outer core as well as the lower mantle region. So that's a temperature gradient here across the core-mantle boundary, and that tells us the amount of heat flux that we have. In the early Earth, it was, like I mentioned earlier, likely much hotter. So at some point, it and then eventually cooled down to this geosome here. So, and we also know that the Earth inner core exists. So at the current stage, we have both thermal cooling, the thermal energy, as well as the compositional or chemical energy sources that power the geodynamo. So now for the core-mantle boundary region, we can actually take the thermal conductivity value of the lowermost mantle materials. Let's just take this value as one exercise here. You can also evaluate that value from the bridge line of perovskite to post-perovskite phase transformation. So that value here, we call it QCMB, is somewhere around 10 to 13 terawatts. Right, so now for a sustainable and thermally driven geodynamo, like I mentioned, we have this QCMB value that's about like 10 to 13 terawatts, and that's also adiabatic conducted heat flow from the outer core to the mantle. And let's call this QA. And we want this QA value to be smaller than this QCB, or QCB larger than the QA. So it's not like there's a huge insulating blanket on top of the outer core heat cannot be conducted away. If this criterion is violated, there's possible thermal stratification in the outer core. All right, so if we now look at that thermal energy source, QA here, this is related to these parameters here, and the key parameter is really the thermal conductivity of the core alloy, and it's also related to the Brunelson parameter and seismic parameter. These values, we know them relatively well, but the thermal conductivity of the constitute alloy is highly uncertain. And let's say if this value is really, really large, say 200 watts per meter per Kelvin, what could happen is that the core has very high thermal conductivity, and so you actually have a very young inner core. So the inner core actually grows relatively fast. So let's just do one exercise here. Let's just take this K thermal conductivity value of ion alloy at about 70 watts per meter per Kelvin. And that would actually give us an isentropic heat flow about QA of about 10 terawatts. Okay, and again, the global heat loss is somewhere around 46 terawatts. So we talk about a number of energy sources. There's thermal cooling and compositional energy sources from latent heat, and also from the release of light elements. And that's also radioactive thermal energy. So all these energy sources then eventually can power the geodynamo. Of course, in the early Earth, when there's no solidification of the inner core, there's no such thing as the compositional energy sources. So, like I mentioned earlier, the Earth core also contains some light elements. We can actually use the physical properties of ion alloys to compare with seismic observations of the outer and inner core. So we know that about like 8% light element in the outer core and likely 4% in the inner core. The exact amount and identity of those light elements are highly uncertain. All these light elements listed here have been considered. So in this study here, I'm going to mainly use silicon as a representative light element to understand the effects of light elements on transport properties. And the reason for me to choose silicon is that not only it's one of the most likely candidates, but it also readily dissolves in solid HCP ion and forms a solid solution system. So it's just much easier for us to use silicon as one candidate light element. So once you actually add light elements, that's melting point depression. So basically the melting temperature of ion decreases depending on the amount and the light elements that you use. So this melting point depression can be as large as about 1,000 degrees. And similarly, if you add light elements as impurity into the ion, the conductivity would actually drop. All right, so how do we actually approach this problem? Let's think about what is contributing to the electrical and thermal conductivity of pure ion to start with. Based on the Winderman-Franz law for pure metals, the major contributor to electrical and thermal conductivity is the electronic contribution or the electron phonon scattering. So you can actually use Winderman-Franz law to relate the thermal conductivity to the electrical conductivity. And this number here is called the Lorentz number or Lorentz constant, which is this value listed here. And that's also this equation here is also temperature dependent. At higher temperatures, though, you can also have electron scattering that contributes to the thermal conductivity. So and you would actually expect the Lorentz number to deviate from the ideal value here. And similarly, if you now add light elements into the system, the thermal and electrical conductivity of ion alloys may not follow Winderman-Franz law. So our approaches here are based on experiments and theories. We do electrical conductivity measurements using 4-probe Van der Pauw method in a laser heated diamond envelope cell, together with in situ X-ray diffraction. We measure the thermal conductivity through time domain thermoreflectance.
Cho today. Mute cam.
I'm sorry. All right, I'm going to continue. And then transient heating. And we collaborated with Ron Cohen and colleagues on first principle calculations. I probably won't speak in details about this, but basically in these calculations, we consider electron phonon, electron, and
unmute the TV.
Light element impurity contributions. All right, so the principle for the electrical conductivity measurement is very simple. Basically, you have a piece of say ion sample that you put it into a diamond envelope cell, and you run current through the sample and determine the voltage change from that, you can then determine the resistance of the sample. Right? But in reality, the experiments are actually fairly tricky because the sample shape and size, as well as the temperature gradient in laser heat dynamo cell. Let me use one example here. This is published by Aurora et al. In 2016. Basically, they use a sample geometry like this. I actually call it two-probe geometry or a pseudo four-probe geometry. And they laser heated a piece of sample. What they found in their results was that the electrical resistivity of pure ion deviates from more ideal temperature-dependent value here. So basically, that's a temperature saturation. The resistivity does not go up linearly with increasing temperature. So if you now use that value and Winterman Franz law, you get a thermal conductivity that is about like 200 watts per meter per Kelvin, basically extremely high. And so then you run into the issue that the Earth's inner core is really, really young, and you in early Earth you don't have a compositional energy source to power the geodynamo and such. So our approach was a bit different. We use a focused ion beam to actually prepare a small piece of sample ion that has the central grid close of about only 6 to 8 micron big. So that actually matches the size of the laser heat beam. So the idea here is actually really follow the parameters in the Van der Pauw method, that you need like kind of a homogeneous sample. You can actually laser heat the whole sample, and the contact regions need to be as symmetric as possible, things like that. So with all that, we also use the flat top laser heating system at GSE cars of the advanced photon source to laser heat the sample from both sides. And you can see the temperature gradient across the sample and from both samples. So the temperature gradient is actually very small. That ensures us that we are indeed measuring electrical resistance from the sample without much influence of the fact. So another thing is to actually make sure that we are indeed measuring the sample from HCP ion and using in situ X-ray diffraction, and there's not only much textures in the sample. So we actually conducted in situ X-ray diffraction experiments. So this is a set of our data at about 105 GPa for the electrical resistance of pure ion in the HCP phase as a function of temperature. So the blue dots here are our experimental data. So you see resistivity goes up linearly with increasing temperature, and that's expected for pure metal. We also did theoretical calculations. Ron Cohen and colleagues did the theoretical calculations in which they consider both electron phonon contribution as well as electron phonon and electron contributions. So it looks like at higher temperatures, the electron contributions become more dominant and account for about like 20% of the conductivity or resistivity. But at relatively low temperatures, electron phonon scattering it's the most dominant mechanism. So for the thermal conductivity measurements, we use pump and probe laser spectroscopy or to be more precisely, time domain thermoreflectance technique. There are two ways that you can actually probe the thermal conductivity. So let's say we use the red arrow here is our pump laser, and you can actually probe the thermal conductivity from the front side or from the back side. To be more precise, we are not really probing the thermal conductivity. In this geometry here, we are actually probing the thermal effusivity. In this geometry here, we are probing the thermal diffusivity, and they are related to the thermal conductivity through these equations here. In this type of measurements, typically we assume the volumetric heat capacity. This term here is constant. There are some theoretical and experimental reports that support this assumption here. So from that, then you can then derive the thermal conductivity from this type of measurements. So this is a representative set of our experiments at high pressure and ambient temperature. The derived thermal conductivity is a function of pressure for pure ion and ion alloys. So you see that actually a significant decrease in the thermal conductivity of ion silicon alloy. This is about like 89% silicon in the alloy, and you see the decrease in the thermal conductivity by a factor of 5. Okay. So this is also expected because of the light element impurity effect. All right, so now let's look at the electrical and thermal conductivity of ion alloys, ion silicon alloys at high pressure and high temperature conditions. So this figure here is probably a bit busy, so bear with me a little bit. The open circles here are the HCP ion data that I mentioned earlier. So electrical resistivity goes up with linearly with increasing temperature. And then even for ion nickel alloy, it also goes up quite linearly too with increasing temperature. But for ion with about 2% silicon, the resistivity increases. Okay, and so if you use Winderman Franz law, then the thermal conductivity is expected to decrease. So for a ion silicon alloy system, we cannot expect the electrical and thermal conductivity to be additive. So you can actually use the data set here from pure ion to 2% to that extrapolate to high pressure, high temperature conditions. Okay, so that's what people generally believe. But when we conducted experiments on ion with 8% silicon, our results are actually quite different. So let's focus on this panel here. Again, the pure ion data for the electrical resistivity as a function of temperature. But for the ion with 8% silicon, and this is also in HCP crystal structure, there's almost no temperature effect. So instead of temperature-dependent resistivity, this is almost temperature-independent resistivity in ion with 8% silicon. So the theoretical calculations by Ron Cohen and colleagues indicate that the reason for this is really the silicon impurity effect that gradually takes over the total scattering that we talk about, especially at high temperatures. And if we now take a temperature of about like 4,000 Kelvin at 136 GPa, that's the pressure at the topmost outer core, then the electrical resistivity of ion silicon alloy is very similar to that of pure ion. Okay, So I think this is like one more unexpected result that we found in this study here. All right, so we went through experimental results and with some values for the electrical and thermal conductivities of ion and ion alloys, ion silicon alloys. We have not really done thermal conductivity and electrical conductivity of other ion like element systems because they are really difficult to prepare. But anyway, so let's use the results from ion and 9% silicon as an exercise to evaluate the magnitude of the adiabatic conductive heat flow QA at the topmost outer core. So this value here, like I mentioned, is actually very similar to that of pure ion. Okay, and so if we take that value, then the QA would be somewhere around 15 terawatts out of the core into the mantle. And that value is actually larger than the current estimate. That's like somewhere around 10, 13 terawatts also. So now we have an energy crisis. We have like, kind of the insulating blanket on top of the outer core. So what could happen is that we can then have thermal stratification of about a few 100 kilometers at the top of the outer core. And this model is actually based on Peter Driscoll's geodynamic calculations. All right, and so we can also think about what is the age of the inner core. Like I mentioned earlier, if the thermal conductivity value is high, then the Earth cools faster, and so the Earth inner core is younger. And again, there are uncertainties not only in the Core-Mantle boundary temperature, but also the thermal conductivity values. But if we just take the values that we just used, and so you can actually calculate the Earth inner core probably started to nucleate at about 1 billion years ago. Okay, so without the inner core, that's only thermal dynamo. And so in the early Earth, the thermal energy source together with radioactive, perhaps other energy sources, power the geodynamo. And at present, at the current time, the thermal compositional energy sources are very important. And I think the amount of compositional energy source is probably more dominant. So we can actually call the current geodynamo the thermal compositionally driven dynamo. All right, so as the Earth core cools, Can you hear me, Russ?
We can hear you.
Yeah,
Hear
okay,
you.
good. Yeah, sorry. Yeah, there was a little bit loss of connection. Yeah.
Okay.
So I was talking about the
Can you reshare your screen?
yeah, sorry. All right, can you see my screen now?
Very good.
Yes.
All right, so I'm going to continue. Sorry about that. So I was talking about the complexities chemically and physically at the lowermost mantle. That can also affect the magnitudes of the heat fluxes across this region here. And I should also note that there are recent discoveries of bridge line, the spin transitions, as well as the post-perovskite in the lower mantle. So we can actually look into how the spin transition, the amount of ion, and
Looks like he's frozen again.
sorry, can you hear me again?
Yeah. You're back.
How about my?
You're
Yeah.
back.
Okay, sorry. Yeah,
And
I'm
reshare
actually
your
I'm at school, but apparently connection is not that great. Yeah. Anyway, so for ferroperite class, there's a spin transition at about 45, 50 GPa also.
You want to reshare your screen?
Yeah. Sorry. Give me a second.
Okay. Great. Good.
All right. Good. So and across the spin transition, the low spin state actually has very high thermal conductivity. On the other hand, bridge line, typically we think it has fairly high sound velocities, but it actually has relatively low thermal conductivity. And our explanation is that bridge line actually undergoes lattice distortions at high pressures that reduces its thermal conductivity. If you now put in more ion into these minerals, the thermal conductivity value decreases with increasing ion content as well. And for the low mantle can also have some subductive slab materials that are made of like basalt or basalt that undergoes phase transformations. One key mineral in subductive slab materials is stishovite, and another one is the nail phase, new aluminum rich phase in the subductive slabs. Surprisingly, stishovite actually has very high thermal conductivity, as high as almost like 80 watts per meter per Kelvin. We can actually compare that to ferroperite class and bridge line, which are like somewhere around like 10 to 40 watts per meter per Kelvin. So stishovite has very high thermal conductivity. The value becomes minimum at the ferroelastic transition and then increases quite significantly in the post-stishovite phase. If you add aluminum impurity of about 5%, the thermal conductivity value decreases by a factor of 2 to 3, but remains relatively high. And for the nail phase, it undergoes the spin transition, and the low spin state also has high thermal conductivity. So if we kind of take that into consideration, it's conceivable that all those effects that we observe because of the spin transition, because of the amount of ion, and as well as the changes in the mineralogy, can actually affect thermal conductivity in the lowermost mantle. Let's use one example for the subductive slabs at the bottom of the lower mantle that consists of certain amount of stishovite. Then you would actually expect to see high thermal conductivity there. If you have more ion-rich regions, perhaps in the large low shear velocity provinces, then the thermal conductivity value is relatively low. So you can actually have variations in the CMB in different regions of the lower mantle. And that can then propagate into the heat fluxes in the Earth outer core. So basically, you can then and then eventually affect the convection patterns and then that to potential magnetic reversals of the Earth Earth outer core. So these are geodynamic calculations by Greg Meyer about 2 decades ago, and he took a number of scenarios into account, basically different heat fluxes values at the core-mantle boundary, and he found that over the different time intervals, like this is actually 3,000 years apart intervals, there are magnetic reversals that can actually occur because of the heat, the variations in the heat fluxes at the core-mantle boundary region. All right, so I'm pretty much almost done with my presentation. So in this presentation here, we mostly focus on understanding the geodynamo of the Earth. We can also think about the dynamos of other planetary interiors, especially the exoplanets that have been discovered recently. There are kind of certain sweet regions in the electrical and thermal conductivity value and the metallic core size here. So it cannot be like, for example, in Stevenson's model here, if you have very low thermal conductivity value, that's potential convection, but not enough to power a dynamo. And so for the terrestrial planets, it's like this is just schematic. So it's like this kind of sweet spot here that a planet can have a sustainable dynamo. All right. So hopefully I provide you some updated knowledge on our understanding of the energy sources that power the geodynamo. And the most direct way now for us is to measure the electrical and thermal conductivity of ion alloys. Certainly we need to kind of expand those studies, not only to say ion oxygen, ion sulfur, or other ternary compounds at high pressure, high temperature conditions, in order to actually have a kind of a better understanding of the scientific problem. Thank you so much for your attention.
Thank you, Afu, for a very comprehensive talk. These are really forefront measurements, and great to see it put in this bigger picture of the geodynamo and the heat flow in the Earth and other planets. So, questions for Afu?
I have a question. Okay, can go ahead, ask. So thank you so much. This was a very interesting talk. So my question is about your pump probe laser spectroscopy to measure the thermoreflectance. Can you expand a little bit on the techniques that you used and how did you take into account the effect of the changes that comes from the diamond anvils?
Yeah, so let me go back to last slide. Yeah, so when I talk about time domain thermal reflectance, there are actually really two approaches that we use. The most traditional way is basically you actually use a pulse laser, you pump, and then you probe, and typically it's actually on the same side. You actually want to call the you want to prepare a piece of sample that is actually really flat and with a well-defined thickness, and then you coat it with, say, aluminum, thin film of a few hundred nanometers, and the probe laser actually probes the changes in the reflectivity of the ion foil. So that's like kind of this interface with conductivity that you need to consider. So typically people use a certain type of mineral oil that with non thermal conductivity under high pressure, so they can actually take that into consideration too. I don't quite understand what you mean by.
No, I meant like,
diamond.
I mean, I wanted a little bit more details about that. What, like, for example, what is the timing of these things? As is it like femtosecond, or and color laser you are using, stuff like that. Sorry.
Yeah. So the traditional way is actually use femtosecond laser, but you can also, like in my lab, I have a picosecond laser that I use for impulsive stimulated light scattering to measure mostly sound velocities. That picosecond laser is also used for the pump probe measurements. We call it picosecond TDTR system. So and we use a continuous wave laser of 532 nanometer to actually as the probe beam. Okay.
Okay. Thank you. Yeah. Okay.
Just to follow up on that, so was this same technique used for the silicates and the oxides? Because here you were talking about iron alloys.
Yes, it's all the same technique. Yeah.
Okay, very good.
Yeah.
I do have a question, if I may ask.
Go ahead, please.
Thank you. By the way, thank you so much for this very nice talk. My question is, you saw the silicon as an impurity in the iron reduces the thermal conductivity. Would you expect the oxygen lowering of ion would even further depresses the thermal conductivity?
Yeah, that's a very interesting question. The short answer is that we don't know experimentally, because the solubility of oxygen in solid ion is very low. So and it's also difficult to quantify the amount of oxygen in your sample. So it's very difficult. But if you think about oxygen as more incompatible, it's not as soluble in ion. So it's possible that you can actually see kind of similar impurity scattering effect that I mentioned for silicon, more like silicon with 89% silicon. However, in earlier theoretical calculations based on DFT calculations, the effect of oxygen is not all that much different from that of silicon.
Okay, thank you.
So you also have some 8% nickel, right?
Yeah.
So it's going to be another factor.
Yeah, so I thank you for asking this question. It's something, in this diagram here, electrical resistivity as a function of temperature for pure ion, and the blue squares here are actually for ion with 10% nickel.
Yeah.
So at ambient temperature, you expect the resistivity of ions nickel alloy to be higher, but eventually at higher pressure, higher temperature conditions, it actually converges with that of pure ion. So you don't expect to see much of an effect on nickel on the electrical conductivity of ion at high PD conditions.
Mm-hmm. And here you're talking about the solid, though, and you need to be considering the fluid, the liquid. As well.
Yeah, yes, I totally forgot to mention about that. So the that's for Earth outer core, certainly we need to actually consider what is the melting effect on the electrical and thermal conductivity. And we actually made an assumption based on theoretical calculations by Ron Cohen, and the change there is about I think like 5 to 10% also.
Okay, good.
Thanks. I believe Rick Seco also has some even newer data across melting, but at relatively low pressure conditions.
Maybe I can jump in.
Go ahead.
Point. Thank you for your talk. Yeah, you're right. I mean, we've got a paper coming out in EPSL. PhD student Miriam Barada has done some work up to 24 GPa on iron 8.5 silicon, and interestingly finds the same sort of flat trends, or at least a low temperature dependence for the iron 8.5 silicon. And on melting, it's really difficult to find a melting signal. So I was going to ask you whether or not you went into the melt, but perhaps it really doesn't matter too much.
Yeah, so we did not go into the melt, and the reason was really because once you actually go into the melt, the sample shape and thickness would actually change dramatically. So your immediate resistance data, I would say it's pretty much useless. But even before that, we can actually approach the melting because of the recrystallization of ion alloys under high pressure, high temperature conditions. And that would actually also affect the values. So basically you can have texturing in the sample that affects your medial resistance. So we typically limit ourselves below the recrystallization temperature.
Thank you.
Geology question.
Thanks.
People found round-shaped boulders all over the world, like 1-2 meters, maybe more. They're almost perfect spherical. What could be origin of these objects? I heard theories people relate them with ball lightning in the core, but it's kind of exotic theory. Do you have another explanation for these objects?
Can somebody help me out? Well, can you repeat your question one more time, or probably explain it in a bit of different way? Maybe
Round-shaped boulders found all over the world. They're almost perfectly spherical. What is origin? What can it be related with electrical thermal conductivity in the core, or?
Those boulders are observed in which regions?
Oh, everywhere. Oh, in our country, in Europe, in Africa, Asia.
And what is the rock type?
I don't know.
Okay, well, that's pretty important for constraining the origin.
Oh, it's types of calcite, but iron also there, also silicon, and also nickel. So basically, whatever you can find in the core.
but they aren't iron dominant. I think the iron or the core hypothesis is probably pretty far-fetched, but you have to know more about the rock type and really study it.
Yeah, but this, yeah, absolutely. But this is a real fact. So these are real objects, and they came from the core from previous ages.
More comments, questions?
So, Afu, I have one question. So, thanks for
Yes.
the very interesting talk. So, I saw you measure some of the silicates at lower mental conditions. I was just wondering. So, when you are doing the thermal conductivity measurements, do you also consider the radiation thermal conductivity, or is that just the phonon or electron components only? Because I remember a few years ago, the radiation thermal conductivity is still something that people are talking about. So I was wondering.
Yeah. So for the ion alloys, the major contributor or the major mechanism is through the electron phonon scattering, right? So the electrons scatter off the lattice, the electron phonon scattering. But in the silicates and oxides, such as ferropericlase and rickymanite, the dominant conductivity mechanism is the phonon scattering. Does that answer your question?
So the radiation thermal conductivity.
So that's the lattice thermal conductivity, right? And so that's what we measure. Lattice thermal conductivity. Your radioactive conductivity can be measured through absorption measurements.
Yeah. Okay.
And there are people doing that. Jung-Fu did some of the measurements.
Yes. Yeah. Okay, thanks.
But that component is typically regarded as relatively small.
Okay, thanks.
I have a quick question. Thank you for the talk. I remember that in 2016, in addition to the ODA paper, there was also the Konakova paper with the diffusivity measurement and a huge difference between the values that they got. And I think in 2018, I believe ODA had another paper explaining that there was an orientation dependence for their resistivity measurements, and that might explain some of the discrepancy between the electrical and the diffusivity methods. But it seems like you might have avoided this. Is this something you took into account, or how else could you explain the disparity between their studies, and how is that something that you avoided?
Yeah, so I think the argument here was that, so in, let's use this piece of sample here. So in the electrical conductivity measurements, you actually measure it in basically along the sample axis, okay? And in thermal conductivity measurements, or Alex Gonchalov's laser flashing technique, you actually measure the conductivity vertically, okay? So if there's textures in the sample, that can actually contribute to the difference between Gonchalov's and OTA's results. One is relatively high, another one is relatively low. So I think the best way is actually to avoid any textures altogether in the sample. So you need to actually have a sample that's prepared in between basically pressure medium, and that is not basically sheared or deformed too much, so you don't have much texture. And I think that's the case in our experiments here. So we can actually avoid that argument. And I think the major issue in OTA's experiments, again, is really the geometry, the sample geometry, that it's not really perfect. So like I mentioned earlier here, Right, so if you now have a piece of sample, let's say it's about like this size, okay, and you only heated a region of the sample. So that's kind of hot part and cold part. So what you are measuring is a combination of the hot and cold contributions. And that's why you are actually seeing this saturation effect here. If it's all hot, then it would actually go up more linearly for pure ion. Yeah. I probably could actually comment on basically the Gancharov's results. I think the main reason for that is probably, you know, the sample in a diamond emerald cell is actually very, very, very small, very, very thin. So if you are off with the thickness estimate, you can actually be off in the thermal conductivity quite a bit. Yeah, but we know we should keep them credit that these are all very difficult, challenging experiments.
Oh, absolutely. Yeah, thank you.
Great. Okay. Any more questions? If not, Apu, terrific talk. Thank you for this very interesting foray into geophysics and mineral physics.
Yeah, it's my pleasure, and I appreciate everybody listening.
Okay. We'll see you all next week.
Bye bye now.